December 21st, 1944. The frozen forests south of Malmedy, Belgium. Oberfeldwebel Klaus Weber crouched in his foxhole as American artillery began its morning barrage. He had survived 3 years of war on the Eastern Front, witnessed the destruction of entire divisions at Kursk, and endured countless bombardments from Soviet Katyushas. Nothing had prepared him for this. The shells were exploding above his head, not impacting the ground as they should, but detonating in midair with surgical precision, 20 to 30 feet above the snow-covered earth. A lethal rain of shrapnel showered down, transforming his foxhole from sanctuary into death trap. The very geometry of survival had been inverted. Weber pressed himself flat against the frozen dirt, feeling hot fragments whistle past his helmet, watching men around him torn apart by steel that seemed to come from everywhere at once. The shrapnel descended from above, targeting heads and shoulders, the parts of the body soldiers instinctively protected least when huddled in defensive positions. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. Multiple fragment wounds were common. The lethality was exponentially higher than anything Weber had experienced in Russia. That morning, examining an unexploded American shell in the pre-dawn darkness, Weber had seen something that defied his understanding of what was possible. The shell's nose fuse contained what appeared to be a complete radio transmitter, roughly the size of a wine bottle, packed with miniature glass vacuum tubes. These delicate components had somehow survived being fired from a gun at forces that should have pulverized them into powder. Wehrmacht engineers had spent a decade concluding such a device was theoretically impossible. The Americans had not only built it but were manufacturing them by the tens of thousands, using them as casually as conventional ammunition. This single realization would fundamentally alter German understanding of what America was capable of producing, and by extension, what Germany was facing. The story of how German soldiers came to witness and fear the proximity fuse began not in the forests of Belgium, but in the laboratories and factories of the United States, where in the summer of 1940, a group of American scientists were tasked with solving what every major power had concluded was an impossible problem. The National Defense Research Committee, formed on June 27, 1940, brought together leading American physicists and engineers under the direction of Vannevar Bush. Among them was Merle Tuve, a physicist from the Carnegie Institution, whose brilliance and volatile temperament would drive a team that eventually numbered over 1,000 scientists and engineers working on what they designated Section T. The problem they faced was straightforward to state but seemingly impossible to solve. German and Japanese aircraft were decimating Allied ships and ground forces. Conventional anti-aircraft guns required either a direct hit, which was extraordinarily difficult against a maneuvering target traveling at 300 miles per hour, or a timed fuse set to explode at a predetermined altitude. In practice, at the start of the war, it required approximately 20,000 shells to down a single enemy aircraft. Some estimates ranged as high as 100,000 rounds per kill. The concept of a proximity fuse had been considered for decades. Make a fuse that could detect when it approached a target and detonate automatically. Simple in theory, impossible in practice given the technology of the 1930s. Germany had explored proximity fuses as early as 1930, developing over 30 different designs, including acoustic sensors that would trigger on engine noise and electrostatic detectors that would respond to charged aircraft surfaces. By 1939, German researchers had concluded the technical challenges were insurmountable. Hitler's leadership issued directives in 1940 prioritizing projects that could reach production within 6 months to support the coming invasion of the Soviet Union. Germany's proximity fuse programs were among the casualties. Rheinmetall Borsig would resume limited work in 1944, far too late to affect the war's outcome. The British had reached further. By 1939, researchers at the Telecommunications Research Establishment had conceived of using a small Doppler radar system. They tested prototypes on rockets, which faced far less severe acceleration than gun-fired shells. But Britain's program was stymied by 2 critical obstacles. The cost was astronomical, and Britain's industrial capacity was already stretched to breaking. More fundamentally, they could not solve the miniaturization problem. The smallest vacuum tubes available, those used in hearing aids, were still far too delicate to survive the violent acceleration of being fired from a gun. By 1941, British scientists had working prototypes that functioned perhaps 50% of the time under ideal conditions. For military use, this was inadequate. The British shared their research through the Tizard mission when America entered the war. But it would be American scientists and American industry that actually made it work. The Americans took the British research and did what no other nation could. They actually built it, not a laboratory curiosity, but a mass-produced weapon that could be manufactured by the millions. Fuze's Section T at what became the Applied Physics Laboratory of Johns Hopkins University, established on March 10, 1942 in a rented Chevrolet garage in Silver Spring, Maryland, settled on a radio-based proximity fuse using Doppler radar principles. A miniature transmitter in the nose of the shell would emit radio waves at approximately 180 to 220 MHz. When these waves struck a target and reflected back, the frequency would shift due to the Doppler effect. When the reflected signal reached a predetermined frequency, indicating the target was within lethal range, an electrical circuit would close and detonate the shell. The theory was elegant. Making it work was another matter entirely. Consider the engineering challenges. The fuse had to fit into the nose of a 5-inch artillery shell, leaving room for 7 pounds of high explosive. Inside this space, engineers had to fit a complete radio transmitter and receiver, a power source, safety mechanisms, and a detonator. All of this had to function in extreme temperatures and survive storage for months. Most daunting of all, it had to withstand the shock of being fired from a gun. When a 5-inch shell is fired, it accelerates from 0 to 2,600 feet per second in roughly 20 feet of gun barrel. This creates an acceleration force of 20,000 times the force of Earth's gravity. Every component experiences a crushing force equivalent to being hit by a sledgehammer. The shell then spins at 25,000 revolutions per minute as it passes through the rifled barrel. And after surviving this violence, the delicate electronics had to function perfectly during the few seconds of flight time before reaching the target. James Van Allen, a young physicist who joined the Applied Physics Laboratory in April 1942 as a founding member, faced the task of developing what the team called rugged vacuum tubes. He started with miniature tubes that Raytheon and Sylvania had developed for hearing aids. These were designed for the gentle environment of sitting in someone's pocket, not the violence of artillery fire. Working with Sylvania Company engineers, Van Allen redesigned the tubes from first principles. The glass envelopes were thickened and carefully annealed. The internal filaments and grids were redesigned with shorter spans and heavier cross-sections. The tubes were potted in wax inside the fuse body, which cushioned them against shock. Every aspect was tested by firing complete fuses from a vertical gun into the ground at the Naval Proving Grounds in Dahlgren, Virginia. The soft earth caught the shells gently enough that researchers could recover the fuses and examine the tubes under microscopes to see what had broken. Through hundreds of test firings and thousands of design iterations, the team gradually developed tubes that could survive. By September 1941, they were achieving success rates above 50%. The Navy, desperate for any improvement in anti-aircraft effectiveness, accepted this failure rate and authorized mass production tooling. The engineers were confident they could improve reliability during the production ramp-up, and they were right. By early 1943, reliability had climbed above 90%, but vacuum tubes were only one challenge among many. The power source presented its own difficulties. The fuse required a battery that could provide sufficient voltage, remain stable during storage, activate instantly when the shell was fired, and survive the 20,000 G acceleration. Standard batteries could not survive gun launch. Liquid electrolyte batteries would rupture under acceleration. Dry cell batteries lacked sufficient voltage. The solution came from an unlikely source. Researchers at the National Bureau of Standards developed a reserve battery using a glass ampule containing liquid electrolyte. The ampule was designed to shatter under the shock of gun launch, releasing electrolyte into the battery cells and activating the battery instantly. The design was elegant. The very force that destroyed conventional batteries now served to activate the specialized battery designed for the proximity fuse. The detonator required equal ingenuity. It had to be safe during handling, loading, and even rough handling in combat conditions. It could not detonate if the shell was dropped or if another shell exploded nearby. Yet it had to fire reliably when commanded by the electronic circuit. Engineers developed a mechanical safety system that remained locked until the shell had traveled a safe distance from the gun, using centrifugal force from the shell's rotation to release the safety. By late 1942, all components had been developed and tested individually. The challenge now was integration and mass production. Over 100 manufacturers would eventually be involved in producing components for the proximity fuse. Eastman Kodak handled overall design coordination. Exide developed the specialized batteries. Sylvania manufactured the miniature vacuum tubes. Dozens of other companies produced resistors, capacitors, detonators, and other components. Each component required precision manufacturing. Tolerances were measured in thousandths of an inch. Quality control was paramount. A single defective component would render an entire fuse inoperative. Workers, many of them women entering industrial work for the first time, were trained to exacting standards. The workforce grew to include thousands of assembly line workers producing components and assembling complete fuses. The first combat test came on January 5, 1943, in the waters off Guadalcanal in the Solomon Islands. 4 Japanese Aichi-D. 3 dive bombers, their obsolete design compensated by pilot skill and determination, completed an attack run against an American task force. The aircraft had struck the New Zealand cruiser Achilles and were turning away with characteristic Japanese precision. Lieutenant Red Cochran gripped the fire control director aboard the cruiser USS Helena as 2 salvos thundered from the ship's aft 5-inch battery. One of the departing Japanese aircraft erupted in flames without being touched, ripped apart by shrapnel from a shell that exploded 30 feet away. The pilot never understood what killed him. Neither did his commanders. Neither would the commanders, Japanese high command for the remainder of the war. This was the first combat kill by a weapon that military historians would later rank, alongside radar and the atomic bomb, in strategic importance. The proximity fuse, deceptively codenamed the variable time or VT fuse to disguise its function, had just announced itself to the Pacific War. Over the next 2.5 years, this technology would fundamentally alter Japanese tactical calculations, shatter their aerial offensive capability, and save thousands of American lives. The effectiveness was immediate and dramatic. Traditional anti-aircraft fire using timed fuses required approximately 2,500 rounds to achieve a single aircraft kill. Proximity-fused ammunition required approximately 600 rounds per kill, a 4-fold improvement. In practice, ships equipped with proximity-fused ammunition demonstrated even better performance. The fuse was credited with 50% of enemy aircraft kills, despite comprising only 25% of ammunition fired, demonstrating a kill ratio 3 times better than conventional ammunition. The impact on naval air defense was transformative. Japanese kamikaze attacks, which had proven devastatingly effective against ships equipped with conventional anti-aircraft ammunition, faced a nearly impenetrable barrier of proximity-fused defensive fire. Ships that would have been lost to kamikaze attacks survived. Operations that would have been delayed or cancelled proceeded on schedule. The westward advance across the Pacific accelerated. But the Pentagon had another target in mind for proximity fuses. Ground forces facing German artillery and infantry formations needed every advantage they could obtain. The challenge was adapting the naval anti-aircraft fuse for use in ground artillery. Naval guns fired 5-inch shells at high velocity from stable platforms. Army artillery fired larger shells at varying velocities from field positions. The fuse had to be recalibrated for different shell sizes, different velocities, and different battlefield conditions. By mid-1943, progress on artillery shells had advanced to the point where a proximity fuse for field artillery was practical. Again, gun characteristics proved challenging, particularly the lower acceleration that howitzers generated compared to high-velocity naval guns. An additional complication was the varying characteristics of different powder charges. Researchers had to cope with 29 different velocities and rates of spin in their calculations. No one had much idea what the best height was for an air-bursting shell. By exploding shells above boards placed on the ground and then examining the shrapnel patterns, researchers found that the optimum damage height varied based on gun caliber. The more common guns, 105mm and 155mm, averaged around 30 feet, while the 240mm howitzer effective burst height was more than 70 feet up. By 1944, the Army had effective shells for most of its guns, but still could not use them. The secrecy edict remained in place at the insistence of the Army Air Forces, which effectively limited use of the proximity fuse to overwater. The Pentagon had decided it was too dangerous to have a fuse fall into German hands because they might reverse engineer it and create a weapon that would destroy Allied bombers, or at least find a way to jam the radio signals. When a ship fired a dud shell that landed on Sicily in 1943, headquarters quickly dispatched a special patrol to find and retrieve the fuse. That restriction began to change in June 1944 as the Germans' V-1 rocket began to make itself felt over England. British and American generals quickly realized the proximity fuse would prove, in Churchill's words, potent against the buzz bombs. At first, they restricted the ammunition to the Army's 90mm anti-aircraft guns and British 3.7-inch guns located along the English coast. The fuse helped increase the proportion of destroyed Vohms second from 24% to almost 80% in about a month. After the Allies captured Antwerp, V-1 attacks shifted to that port, forcing the combined chiefs of staff to realize the time for total secrecy was over. On October 25, 1944, the combined chiefs of staff approved the use of the proximity fuse over land. The most immediate use of the special shells on the European continent was by anti-aircraft guns set up along the V-1 approaches to Antwerp. By the end of the war, they had accounted for more than 2,000 V-1 kills. The release of artillery shells for ground combat took longer. The Ardennes offensive provided the final incentive. Early on the morning of December 16, 1944, the commander of the U.S. 406th Artillery Group, Colonel George Axelson, had a difficult decision to make. The Germans had just launched the offensive that would become known as the Battle of the Bulge, and one of their first targets was the 38th Cavalry Squadron, dug in around Monschau, Germany. The lightly armed cavalry troopers needed help, and the commander quickly called for artillery support from the 406th. Axelson had just received a new, secret artillery shell. The problem was that Allied Commander Dwight Eisenhower had not yet given permission to use the weapon over land where the Germans might capture an intact fuse. Axelson decided that the emergency trumped the restrictions and ordered his gunners to use the new shell. Minutes later, rounds equipped with proximity fuses started exploding right over the heads of the attacking Germans. The effect was immediate and catastrophic for the German forces. Soldiers who had survived years of combat on the Eastern Front, who had learned to take shelter in foxholes and trenches during artillery barrages, discovered that their hard-won survival skills were now worthless. The shells exploded above their positions, showering down fragments that penetrated from above. There was no defense. Foxholes became graves. On December 19th, 3 days after the 406th Artillery Group broke the embargo, Eisenhower formally asked for clearance to use proximity fuses across the front. 2 days later, all restrictions were removed. Unfortunately for the troops commanded by SS Colonel Otto Skorzeny, it was just in time for their attack on the town of Malmedy. American artillery battalions supporting the town fired the proximity fuse to great effect, so unnerving the attackers that some charged directly into the artillery fire, yelling "Kamerad," the German word for comrade used to signal surrender. The psychological impact was as devastating as the physical destruction. German soldiers had experienced artillery fire for years. They understood its dangers and had developed tactics to survive it. But proximity-fused artillery was different. It rendered conventional defensive measures obsolete. As early as December 23rd, estimates had as many as 2,000 German soldiers being killed by proximity-fused rounds. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The German army quickly learned respect for the fuses. An American intelligence report noted German commanders offered a reward for soldiers who found a surviving fuse. Prisoners of war repeatedly spoke of the demoralizing effect of artillery airbursts, particularly at night. The airbursts had the added effect of cutting enemy communication wires more easily. General George Patton wrote enthusiastically about the weapon's effectiveness. On the night of December 25th and 26th, his Third Army had used the new proximity fuse on a concentration of Germans near Echternach and actually killed 700 of them. In another engagement, Patton's forces caught a German battalion attempting to cross the Sauer River, with a battalion concentration fire mission and killed by actual count 702 soldiers. Patton wrote to the War Department, "The new shell with the funny fuse is devastating. I think that when all armies get this shell, we will have to devise some new method of warfare. I am glad that you all thought of it first." The effectiveness stemmed from the fundamental physics of airburst artillery. When a conventional shell impacts the ground, much of its explosive energy is absorbed by the earth. The blast creates a crater, and shrapnel is projected primarily outward in a cone pattern from the impact point. Soldiers in foxholes or behind cover are relatively protected, but when a shell detonates 30 feet above the ground, none of the explosive energy is wasted on cratering. All of the energy goes into producing a blast wave and accelerating shrapnel downward and outward. The shrapnel pattern from an airburst covers far more area than a ground burst. A single proximity-fused shell could incapacitate soldiers across an area of several thousand square feet. Multiple shells fired in a time-on-target concentration could blanket an entire zone with lethal fragments. Soldiers caught in the open faced near certain death or severe injury. Even soldiers in foxholes were vulnerable, as fragments descended from above into positions designed to protect against horizontal fire. The psychological impact was profound and multifaceted. German soldiers understood probability. They knew that artillery fire was dangerous but survivable with proper precautions. Take cover, stay low, wait for the barrage to pass. These tactics had been developed over years of combat and reinforced through survival. But proximity fuses inverted this equation. The harder soldiers pressed themselves into their foxholes, the more confined and vulnerable they became to descending shrapnel. German tactical doctrine had evolved around concentrated formations. Units moved together, fought together, provided mutual support. Proximity fuses made concentration deadly. A single well-placed shell could devastate an entire platoon. To survive, forces had to disperse widely, but dispersion reduced combat effectiveness and made coordinated operations difficult. German commanders faced an impossible choice: concentrate and risk annihilation from proximity-fused artillery, or disperse and lose tactical effectiveness. The sense of helplessness broke the will to resist in ways conventional artillery never did. Soldiers could accept danger when they had some chance of survival, some action they could take to improve their odds. But against proximity-fused artillery, there was nothing they could do. No foxhole deep enough, no cover thick enough, no evasive action effective enough. American intelligence reports noted that German prisoners increasingly cited artillery as the primary reason for surrender. Not the fear of death, which soldiers accepted, but the specific fear of proximity-fused artillery, which provided no chance of survival and no way to fight back. The final months of the war saw some German units essentially paralyzed by fear of American artillery. Units would not move during daylight. They avoided any position that appeared to be a likely target. Morale plummeted as the material reality of American industrial and technological superiority became undeniable. This was psychological warfare at its most effective, accomplished not through propaganda, but through demonstrated technological dominance. By March 1945, As Allied forces prepared to cross the Rhine and advance into Germany, proximity-fused ammunition had become standard for all American artillery. Factories were producing fuses faster than they could be shipped to Europe. At peak production, the American electronics industry manufactured 70,000 fuses daily. The cost per fuse had dropped from $732 in 1942 to $18 by 1945 as production techniques improved and economies of scale took effect. The Germans never developed effective countermeasures. Electronic jamming was theoretically possible, but required understanding the fuse's operating frequency and characteristics. Without intact working fuses to analyze, German engineers could not determine the specifications needed for jamming. Even if they had, deploying jammers across every potential target would have been impossible given Germany's collapsing industrial capacity and supply situation. Physical countermeasures were equally ineffective. The fuses operated by detecting reflected radio waves. Reducing the radar cross-section of troops and equipment was impossible. The human body itself reflected enough energy to trigger the fuse at close range. The only defense was dispersion, spreading forces widely enough that a single shell would not catch multiple targets. But dispersion reduced combat effectiveness and made coordinated operations difficult, further degrading German tactical capabilities. Wehrmacht veterans interviewed after the war consistently described the proximity fuse not merely as a clever weapon, but as a demonstration of comprehensive superiority in science, industry, and national will. The fuse represented everything that made American industrial power dominant in World War II. It combined advanced technology with practical engineering. It required massive investment but produced proportionate results. It was sophisticated yet manufacturable, effective yet affordable at scale, innovative yet reliable. Post-war analysis by military historians identified the proximity fuse as one of the key technological advantages that shortened the war. Estimates suggest the fuse saved tens of thousands of Allied lives by reducing the length of campaigns and increasing the effectiveness of defensive operations against kamikaze attacks in the Pacific. In Europe, proximity fuses were credited with preventing the German Ardennes offensive from achieving its objectives, contributing to the rapid collapse of German resistance in the spring of 1945. The strategic impact was multiplied by production scale. By the war's end, American industry had produced over 22 million proximity fuses, each containing approximately 130 precision components. Because fuses were available in unlimited quantities by late 1944, they could be used without conservation. Fire missions that would have been questionable with conventional ammunition became routine. Suspected enemy positions could be saturated. Defensive fire plans could cover vast areas with overlapping patterns. The psychological effect of this abundance was as significant as the physical effect. German soldiers facing American artillery understood implicitly that they were fighting an enemy with capabilities beyond their ability to match or counter. The proximity fuse ended their war not through any single dramatic defeat, but through the accumulated weight of countless engagements, each proving the same lesson. They were fighting an enemy whose industrial capacity could produce technological miracles by the millions. The technological legacy of the proximity fuse extended far beyond military applications. The miniaturization techniques influenced the entire electronics industry. The quality control methods became standard practice in manufacturing. The workforce training programs demonstrated that complex technical work could be performed by people without advanced education, given proper training and supervision. The space program drew directly on expertise developed during the proximity fuse program. James Van Allen, who had designed the rugged vacuum tubes, became one of the founding figures of space science. The Van Allen radiation belts surrounding Earth bear his name. The miniaturization and shock-hardening techniques developed for proximity fuses informed the design of instruments for rockets and satellites that had to survive launch forces and function in the harsh environment of space. The development of computers benefited from advances in electronics manufacturing. The concept of mass-producing complex electronic devices to exacting standards, proven feasible by the proximity fuse program, enabled the later production of computers and consumer electronics. Supply chains established for Fuze components supported the growth of consumer electronics markets in the post-war era. The scientists and engineers who worked on the Fuze went on to distinguished careers. Fuze returned to the Carnegie Institution after the war, rarely speaking publicly about his role developing proximity fuses. When details were finally released, Fuze deflected personal credit, emphasizing the contributions of hundreds of engineers and thousands of production workers who transformed theoretical concepts into millions of reliable fuses. The story of the proximity fuse is ultimately a story about resources, priorities, and the different paths nations took through World War II technology development. Germany invested heavily in advanced weapons like jet aircraft and ballistic missiles. These were impressive achievements but came too late and in too few numbers to affect the war's outcome. America invested in technologies that could be mass-produced immediately. Proximity fuses, while sophisticated, were designed from the start for mass production. Every decision in their development prioritized manufacturability and reliability. This reflected a fundamental difference in strategic thinking. Germany sought war-winning superweapons that would offset Allied numerical superiority. America sought effective weapons that could be produced in quantities that made numerical superiority overwhelming. The proximity fuse was not a superweapon. It was a very good weapon produced in very large numbers. That approach proved decisive. The proximity fuse stands as testament to what free societies can achieve when they combine scientific excellence with industrial might and unwavering determination. It proved that the greatest victories come not from seeking the impossible, but from making the necessary possible through sheer force of will and unlimited application of resources. The German soldiers who faced proximity-fused fire understood this implicitly. They reported not that Americans had developed a clever trick, but that Americans possessed capabilities fundamentally beyond Germany's ability to match. Oberfeldwebel Weber, who had examined that unexploded proximity-fused shell in the pre-dawn darkness of December 21, 1944, survived the Battle of the Bulge. Captured in January 1945 as German forces retreated eastward, he spent the remaining months of the war in an American prisoner of war camp. In post-war interviews, Weber described the proximity fuse as the moment he understood Germany had lost the war. The theoretical possibility of Germany developing advanced weapons no longer mattered. What mattered was the reality of American factories producing millions of sophisticated electronic devices, each one capable of turning a single artillery shell into a weapon of unprecedented lethality. What mattered was the demonstrated capacity of American industry to solve problems German engineers had declared impossible, then manufacture the solutions at a scale that made them commonplace rather than rare. The weapon that had seemed impossible to build became the weapon that changed warfare. American scientists, engineers, factory workers, and military personnel had accomplished what the world's experts declared could not be done. They had miniaturized complex electronics, made delicate vacuum tubes survive artillery forces, and manufactured the result by the tens of millions. The proximity fuse proved that sometimes the most important advantage in war is not tactical brilliance or strategic innovation, but the simple, overwhelming capacity to produce effective weapons faster than the enemy can adapt to them. The final irony of the proximity fuse story lies not in its technical sophistication, but in its ordinariness by war's end. What had begun as an impossible dream in 1940 became routine ammunition by 1945. Gunners loaded proximity-fused shells without ceremony, fired them without special training, and expected them to work without question. The miraculous had become mundane through the sheer scale of American production. This transformation represented a uniquely American approach to warfare, where European military traditions emphasized the exceptional, the heroic individual weapon or tactic that might turn the tide of battle. American doctrine emphasized the systematic, not the brilliant stroke, but the overwhelming application of adequate solutions produced in quantities that made excellence through volume rather than rarity. The proximity fuse embodied this philosophy perfectly. German military theorists had spent decades developing concepts of quality over quantity, believing that superior training, superior tactics, and superior weapons could compensate for numerical inferiority. The Eastern Front had already begun to shatter this illusion as Soviet production overwhelmed German forces through sheer mass. But Soviet weapons were often crude, their effectiveness achieved through volume alone. The proximity fuse demonstrated something more threatening to German military thought. American weapons were both numerous and sophisticated, combining quality and quantity in ways German industry could not match. The psychological impact extended beyond individual soldiers to German military leadership. Intelligence reports cataloging American proximity fuse use forced German commanders to confront an uncomfortable reality. The technological gap was not narrowing but widening. While Germany struggled to produce sufficient conventional ammunition, America was replacing conventional ammunition with sophisticated electronic weapons. While German factories labored to maintain production of established weapon systems, American factories were pioneering mass production of devices that had existed only in laboratories 2 years earlier. This realization influenced German decision-making in the war's final months. Some commanders advocated fighting to the last man, believing fanatical resistance might extract such a price that America would negotiate rather than pursue total victory. But others understood that proximity fuses represented just one example of American technological and industrial superiority. If America could mass-produce proximity fuses, what other weapons might be waiting? What other impossibilities had American scientists and engineers transformed into reality? The atomic bomb, still months away from deployment when proximity fuses first devastated German forces at the Battle of the Bulge, would provide the ultimate answer to that question. But in many ways, the proximity fuse was more psychologically devastating than atomic weapons. The atomic bomb was singular, unique, a weapon of such magnitude that it existed outside normal military calculations. The proximity fuse was ordinary artillery made extraordinary. It suggested that American technological superiority extended across the entire spectrum of warfare, from the exotic to the commonplace. German prisoners interrogated about proximity fuses consistently demonstrated a particular form of demoralization. They had not been defeated by superior tactics or superior courage. They had been defeated by superior production capacity applied to superior technology. There was no shame in losing to a better soldier, but there was profound despair in losing to a better factory. The proximity fuse forced German soldiers to confront the reality that individual courage, tactical skill, and operational excellence could not overcome industrial inadequacy. This lesson would resonate through military thinking for decades after the war. The proximity fuse demonstrated that modern warfare required not just military excellence but industrial excellence, not just tactical innovation but production innovation, not just brave soldiers but productive economies. Nations that could not match American industrial capacity would need to find asymmetric approaches to warfare, because symmetric competition would inevitably favor the side that could produce sophisticated weapons in overwhelming quantities. The proximity fuse also revealed the importance of scientific research applied to military problems. The German decision in 1940 to cancel proximity fuse development because it could not be completed within 6 months proved catastrophically short-sighted. That decision prioritized immediate production over future capability, tactical expediency over strategic investment. America made the opposite choice, investing heavily in research that would not produce immediate results, but would provide decisive advantages later in the war. This difference in approach reflected deeper differences in strategic thinking. Germany's military culture emphasized operational art, the brilliant campaign that would achieve decisive victory through superior execution of military operations. America's military culture increasingly emphasized industrial art, the systematic production of material advantage that would make operational brilliance unnecessary. Both approaches had merit, but only one was sustainable in prolonged industrial warfare. By May 1945, when Germany surrendered unconditionally, proximity fuses had become so commonplace in American arsenals that they barely merited mention in after-action reports. The weapon that had seemed impossible to build just 5 years earlier was now simply another line item in ammunition expenditure reports. This transformation from impossible to ordinary in such a short period captured the essence of American industrial power in World War II, the capacity to make miracles routine, to transform laboratory curiosities into mass-produced weapons, to solve problems declared unsolvable through the application of sufficient resources and determination. The proximity fuse stands as testament to what can be achieved when a free society mobilizes its scientific, industrial, and human resources toward a common purpose, proving that sometimes the most devastating weapon is not the one that inspires fear, but the one that inspires despair. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.